how do we find inverse transforms? Well, we can use our table for some very simple cases, but in general, in order to find an inverse transform of more complicated Laplace transforms, we're going to use a method of partial fraction expansion. This allows us to expand a ratio of functions in S as a sum of much simpler functions, which hopefully we can then find in our table, and then find the corresponding inverse Laplace transform of the individual pieces. So you've covered this method in circuits 2. So I'm not going to go into much detail. I'll review using just a few example problems. The method is covered in section B.5 of your textbook, so if you want to go back for a more in-depth review. There are a couple of common cases that you'll run into depending on the form of the roots of the polynomial that is in the denominator of the rational function. So here, let's take a look at an example in which we have distinct real roots. So this might be an example Laplace transform function. I want to factor the denominator, if I can. Here it's a second order example, so I could use the quadratic formula to find the roots. In this case, the roots are s equal to 3 and s equal minus 2. Okay. In this case, and this would be extended if I had 3 or 4 roots, I can write the expansion then like this, where I have as yet unknown constants in the numerator. That I'll call K1 and K2. We can evaluate K1 by looking at the left hand side and the right hand side here, and I can evaluate K1 by multiplying both sides. In this case, I want to multiply both sides by the denominator of my K1 term. So I'll multiply both sides by s minus 3 x of s, and then I'm going to evaluate this at s equal to 3 at the corresponding root of the denominator. I see that on the left hand side here, when I multiply by s minus 3, the s minus 3 term will cancel in the denominator, and then I just evaluate the rest of this expression at s equal to 3. So I'll have 21 minus 6 here in the numerator, or 15, and then I'll have s plus 2 or 3 plus 2 or 5 in the denominator. So this reduces to 3, and so that gives us our K1 term. Similarly, K2, multiply both sides by s plus 2. Evaluate this now at minus 2. And when I multiply this by s plus 2, the s plus 2 term will cancel in the denominator. I evaluate this at s equal to minus 2. I'm going to get minus 14 minus 6 in the numerator, and here evaluating at s equal minus 2, I'll have minus 2 minus 3 or minus 5. Okay. And so this will give me a minus 20 divided by minus 5, or a 4 for K2. It didn't completely explain what happens when we multiply both sides here, but when I multiply both sides by s minus 3, here I'm left with just the K1 term. And when I multiply the k2 term, which is k2 over s plus 2 times s minus 3, and evaluate that at s equal to 3, that term goes away. It will go to 0. So I'm just left with k1 on the right-hand side. So k1 is just equal to the left half side after I eliminate the corresponding denominator term and then evaluate it at the root. Sometimes this is called the cover-up method, because one common way of doing this is actually just putting your finger over this term on the left-hand side, the s minus 3 term, and then evaluating at s equal 3. And similarly, I could find the k2 term by just covering up on the left-hand side this s plus 2 term and evaluate the rest of the expression then at s equal to minus 2 and directly get k1, or I'm sorry, k2. And then, so now I can write x of s in this simpler form. It would be k1 over s minus 3 plus 4 over s plus 2. You can do a simple check here, and it's usually wise because I'll just evaluate this at s equal to 0. I can't evaluate it at one of the roots because the term goes to infinity. So I pick a non-root value for s, and I see here in my partial fraction expansion that when I evaluate this at s equal to 0, I just picked s equals 0 because it's simple to evaluate. I have minus 1 plus 2 or 1. If I evaluate my original function at 0, I'm going to get minus 6 over minus 6, which is also equal to 1. So it's a check. I've verified it at verified that the expansion is equal to the original function at one value of s. It's certainly no guarantee that I've done this arithmetic correctly, but it does verify that the mathematics. Now that I've got the Laplace expansion, let me just write over here before I go to a new board, the corresponding inverse Laplace transform. Both of these terms are in my table of Laplace transforms, so I can find the inverse Laplace transform. It would be 3 e to the 3t u of t. That's the Laplace transform of this term. And then I'm going to have plus 4 e to the minus 2t u of t, corresponding to this second term. So this would be the corresponding inverse Laplace transform of this original function. In order for our partial fraction method to work, you've got to make sure that you're dealing with a proper ratio or a proper function, one in which the order of the numerator is less than the order of the denominator. So here's an example in which the numerator and denominator are of equal order, and I can factor the denominator, in this case as s plus 1 times s plus 2, and a common mistake here is to then just go to a partial fraction expansion and say, well, I'll have a k1 over s plus 1 term plus k2 over s plus 2 term. This gives you an incorrect result. Again, we can do the division here to actually determine that the constant term in front is actually 2, so just determine that by synthetic division. And so this is the proper form of a partial fraction expansion of an improper ratio. Then we could again find k1 and k2 by our lookup method. Can multiply both sides by s plus 1, and evaluate it at s equal to minus 1. And this term would go away. We'd be left with just this last term would go away, and we'd be just left with k1 on the right hand side. So k1 is equal to, on the left hand side, I'm just going to cover up the s plus 1 term, or pretend it's not there, and evaluate the rest of this at s equal to minus 1. So in the numerator I'll have 2 times minus 1 squared plus 5, and in the denominator I'll have minus 1 plus 2. So I'll get here 7 over 1, and so for k1 I find it's equal to 7. K2, again, cover up the s plus 2 term, evaluate the rest of this at s equal to minus 2. So I have 2 times minus 2 squared plus 5 over minus 2 plus 1. And so here I'll get 4, 8, 13 in the numerator, minus 1, and so I'll get minus 13 as the result here. And so my partial fraction expansion of x of s is 2 plus 7 over s plus 1 minus 13 over s plus 2. If I hadn't done the synthetic division to find the constant part here, I would have gotten just this part for my partial fraction expansion. Of course, that's incorrect. If I add these together, I'm not going to get my original function. Again, a quick check here is evaluating at just one value of s. I could also well, let me try s equals 0 here. In this case, from the partial fraction expansion, I'm going to get 2 plus 7, and then I'll get minus 13 halves. So that actually simplifies to 5 halves. Plugging s equal to 0 into the original function, we see it reduces to 5 halves as well. So again, that's one check. I could try it at another value of s, perhaps s equal to 1. Again, I can't choose s equal to minus 1. That's one of the roots of the denominator and would cause the expression to go to infinity. Now that I've got the partial fraction expansion, again, I can refer to my table to find the inverse transform. You'll see that a constant actually inverse transforms as an impulse. So I have 2 delta t, and then plus 7 e to the minus t u of t, and then finally minus 13 e to the minus 2t u of t for the result in this improper fraction case.